which is the challenge? All the traditional seismic device have too many limitations. The first is that they primarily focus on preventing the structural collapse, often neglecting the post-earthquake recovery aspect. So this has a big economic impact, because the functionality of the building is compromised, and so we need a high cost for the post-earthquake intervention. So we need an engineering solution that can have self-centering capabilities. That is the ability of the structure to return to its original position, and the energy dissipation to prevent to protect the building from the earthquake. So we need a new device that can face this challenge and overcome this limit simultaneously at the same way. And shape memory alloys are one of the possible solutions to overcome these limits, thanks to their property, that is the superelasticity. The superelasticity, as you probably know, is the ability of the alloy to have large recoverable strains up to 8%, and return to their original shape upon unloading. And it is due to stress induced phase transformation between the austenite, that is the high temperature and order phase, and the martensite, that is low temperature phase. This transformation of phase that is under stress make this alloy have this flag-shaped hysteresis behavior when subject to stress. And thanks to this kind of curve, they have the ability to dissipate the energy during the loading and unloading, and to have self-centering capability, because we have minimal residual deformation after the stress strain. So we used shape memory alloys to propose a new model of seismic joint. We build it. So as you can see, this is a model of joint, just to test, and it is made by two L-shaped nitty sheets that work in parallel, one here and the other on the other side. And this was the first configuration that we statically test, and we propose in this presentation. Then we tried to test another configuration to make a comparison. That is this second one, that merge two nitty sheets with L shape that are this one, with these springs, these helical springs that are made of nitty shape memory alloys. And our experimental approach covered three different phases. First, we tested the single sheet Then we moved in testing the first configuration of joint, then the second, and then we test another joint that is like the first one, but with sheets that are made of steel, just to have a comparison between the common steel performances and the shape memory alloys one. So moving in detail in materials and method, here you can find all the specification of the material used, that are sheets here and wires. And you can see in particular that we use the super elastic alloy at room temperature. The manufacturer said that they had an austenite finish of 5 degrees Celsius. So we are sure that they are super elastic at room temperature. And then the shape memory alloys and springs underwent shape setting treatment in a furnace. That is this one, the furnace of the laboratory, at 500 degrees Celsius for 30 minutes. And then they were water quenched to acquire this cell form, because they had no anal form. They acquired it through the shape setting heat treatment. Then we drilled heat to ball connection in the joint, and we tested the single sheets and the joint using a universal tensile testing machine equipped with a 50 kilonewton loading cell, and under displacement control. The testing rates were 20 millimeter per minute in the when we tested the single sheets, while the joint, so the assembly, was tested at 5 millimeter per minute, the formation rate. And we built a special test matrix with a total of 28 tests, starting from the individual sheet to the 3 assembly configurations. And we test the whole at 2 different temperatures. The temperature of the environment, that was 25 degrees Celsius, and 100 degrees Celsius. Before talking about results, I show you one of the 28 graphs that we obtained from this kind of tensile testing. You can see how the sheets have the flag-shaped diagram with hysteresis loop, which we talked before. And here I reported the definition of the key performance indicator that we will mention after. In particular, as performance indicator, we use the peak force, that is commonly the maximum load capacity, the energy dissipation, that is simply the area of the loop, the stiffness, that is the very first initial slope of the curve of force displacement, and the volumetric energy density, that is maybe the most important parameter to analyze. Let's note that all the tests were static tests, and because we did it last as a baseline, just to build the joint and to test the static parameters. So they are not dynamic testing that will be made in a following validation test that we will do in following days. What we found, talking about, let's talk first on the individual sheet characterization. We found these two experimental laws. I don't know if you are able to read, but I can say you that we found that the sheets have a quadratic force displacement relationship. So it's true that the sheets are super elastic at ambient temperature. Then once we characterized the sheets, we scaled up and moved in characterizing the assembly performance at at ambient temperature and at 5 millimeters per minute rate. And what we found are the value reported in this table that say that force scales near proportionally with the displacement, while the energy density increases more than proportionally with the deformation amplitude. So in this way, we had a very first systematic validation of the approach. Then we moved in comparing the results of performance that we obtained for the three configurations mentioned before. In particular, we can see that we can find from the data in the table that there is no best configuration, but the optimum configuration depends on the application. For example, the second configuration, that is the L shape plus spring, is the force leader, while the L shape was the most balanced and still, as we can imagine, was the leader on stiffness. So the conclusion from this very first test is that each configuration optimizes at different parameters. So there is no an optimal one, but it depends from the application. And then we moved to a comparison on temperature, and we made it on the first configuration that demonstrated to be the most balanced between the three. And we found that this joint, as we know, is very, very sensitive with temperature, because we found a force enhancement up to 121% with temperature. So the temperature is a parameter to taking into account and to optimize for the next design of the final seismic device. So let's move to the conclusion. In our work, we developed a very first prototype of seismic joint that exploits shape memory alloys as active part. And we made a very first statistical characterization of the single sheet and of the joint in three configurations through 28 tests and different temperatures. And we set the base for the next phase, that is the most important one, that regards the dynamic validation of the seismic joint, using, for example, the shaking table or fatigue machine. These tests are planned starting from this month. So I hope in the next future to present all the results about the dynamic validation of the joint. Many thanks.